In 2022, a truly remarkable picture was released. Why is it so remarkable? This image stands as one of the most detailed radio views ever captured of our galaxy's core. It was pieced together from the inaugural full-array survey conducted by the MeerKAT Radio Observatory in South Africa. Completing this image required 3 full years of data analysis. What it reveals is something utterly strange. Hidden within the violent turmoil at the Milky Way's heart are hundreds of highly organized, thread-like structures, stretching in one dimension. They hang mysteriously above and below the galactic center. These puzzling filaments can extend for as much as 150 light-years, yet they are only 1 to 3 light-years wide. The major question is, what exactly are these enormous, peculiar strands? Scientists are now analyzing this MeerKAT image to find the answers. The center of the Milky Way, located 27,000 light-years from Earth, is a violent place. This innermost area, known as the central molecular zone, stretches across 1,600 light-years. By every measure, it is the most extreme region of our galaxy. The density, temperature, and level of turbulent motion here are roughly 10 to 100 times greater than anywhere else in the galaxy. The energy density from cosmic rays, which indicates high-energy activity, is hundreds to thousands of times higher. It is a hotbed of cosmic action, from the birth of new stars to the explosions of dying ones as supernovae. And of course, there is Sagittarius A star, the supermassive black hole at the very center, with a mass 4 million times that of our Sun. These conditions are incredibly exciting for astronomers, but they also make the galactic center extremely difficult to observe. Visible light cannot pass through the thick clouds of dust and gas. Therefore, researchers use other parts of the electromagnetic spectrum to see through the veil and uncover the secrets at the galaxy's core. Radio waves have the longest wavelengths on the electromagnetic spectrum, ranging from a few millimeters to hundreds of kilometers. Wavelengths from millimeters to tens of meters are perfect for radio astronomy. They pass right through the obscuring clouds, giving us a clear view of what lies beneath. Back in the early 1980s, a PhD student named Farhad Yusef-Zadeh was using the Very Large Array telescope in New Mexico to create a radio map of a section of the galactic center. He intended to study star-forming regions, but narrow bands of radio emission were streaking across his entire survey area, cutting right through the parts he wanted to examine. He assumed these were artifacts or errors in the data, something every scientist finds highly frustrating. After much aggravation and no success in fixing these apparent problems, he returned to the telescope to image the same area at a different radio frequency. That is when he had his breakthrough moment. Early one morning at 4 a.m., while comparing the two samples taken at different times and wavelengths, he saw the same structures in both images. These were not artifacts. This was a genuine discovery, something unlike anything he or anyone else had encountered before. He was seeing highly ordered structures in a place where only chaos was thought to exist, and they had some very unusual traits. Their enormous scale was the most striking feature. These were continuous, narrow ribbons of radio emission, 50 to 100 light-years long but only 1 to 3 light-years wide. They dangled vertically above and below the central molecular zone, the most extreme part of the Milky Way. Some appeared in pairs or clusters, running parallel to each other like the strings on a harp, each separated by a consistent distance of about 1 astronomical unit, which is the distance from Earth to the Sun. When he checked this data against infrared observations from the same area, he found they had no counterpart in that part of the spectrum. This told him they were non-thermal emissions, meaning they were not produced by heated gases. Other measurements, like spectral index and polarization, supported this. They showed the filaments were highly magnetic and were emitting synchrotron radiation. Synchrotron radiation happens when electrons moving near the speed of light interact with a powerful magnetic field. This raised a big question. What could possibly accelerate electrons to such incredible speeds? The emissions were continuous along the entire length of the structures, which ruled out localized events like star formation or supernova remnants. So he named them non-thermal filaments and suggested they were likely connected to phenomena on a galactic scale. His observations did not match anything else known in the galaxy, and many questions remained. Where did these filaments come from? What kept their linear shapes over such vast distances of space and time? And why, when they clustered together, were they so evenly spaced? But almost as soon as this amazing discovery was made, progress stalled. The telescopes available at the time simply weren't sensitive enough to provide answers. Over the next 35 years, only a small number of other vertical non-thermal filaments were found and studied. Some were even given intriguing names like the snake, the pelican, and the bent harp. Sadly, there just wasn't enough data to make significant progress in understanding them. That is, until 2022, and the astonishing image from MeerKAT. The MeerKAT radio telescope at the South African Radio Astronomy Observatory consists of 64 linked antennas. Each antenna has a parabolic dish 13.5 meters in diameter, spread across 8 kilometers of a specially designated radio quiet zone. Built over 4 years, the full array began operations in 2018. Its location in the southern hemisphere is ideal for viewing the center of the Milky Way, thanks to the axial tilt of our Sun relative to its position in the galaxy. This gives MeerKAT a direct line of sight into the central molecular zone and the galactic core. Over 3 years, an international team led by Dr. Ian Haywood, which included Yusef-Zadeh, now a professor at Northwestern University, pointed MeerKAT at a portion of the galaxy covering 6.5 square degrees. This section of the sky is about 30 full moons wide, with Sagittarius A star right at its center. Using L-band radio frequencies from 856 to 1712 MHz, equivalent to wavelengths of 18 to 35 centimeters, they divided this area into a 20-part mosaic. The telescope surveyed each section in turn, accumulating a total of 144 hours of observation time. This was the first time MeerKAT's full array was used, with 60 to 62 dishes collecting data at any one moment. The process generated 70 terabytes of raw data, equivalent to 700 hours of 4K YouTube content. Processing this data was a massive challenge. This is a common edge smoothing method used to remove background noise and enhance the visibility of fine details, which was especially important for seeing the non-thermal filaments clearly. And this is the final result. It looks more like a piece of art than a scientific study, capturing a wealth of features. Some are well known, like Sagittarius A star, seen in the bright central area. The image also provides clearer views of previously known supernova remnants and star-forming regions. One object visible is a supernova remnant. As the research team noted, one of the most startling discoveries was the sheer number of filaments visible in the image. There were 10 times more than all previously known filaments combined, most of which had never been seen before. This was a game changer. There was finally enough data to conduct meaningful population studies. The team got to work performing statistical analysis on the filaments. This research, published in the astrophysical journal Letters, not only describes the filaments in greater detail, but also offers intriguing clues about their origin. The new data confirmed that all the filaments are magnetized. In fact, the team found the magnetic field was significantly stronger, in some cases 10 to 100 times stronger, than typical galactic magnetic fields. The new analysis also confirmed that synchrotron radiation is a defining feature. This means the filaments appear to cool as they stretch away from the galactic plane. This offers a clue to their possible origin. The electrons farther from the galactic plane could be older, suggesting the filaments are related to past activity of Sagittarius A star. There was another clue pointing in this direction: enormous structures known as radio bubbles, first discovered by Farhad Yusef-Zadeh and the MeerKAT team in 2019. These huge radio-emitting structures stretch symmetrically above and below the galactic plane, forming an hourglass shape thousands of light years across. They are thought to have been created by a phenomenal outburst from Sagittarius A star between 100,000 and 1 million years ago. An event powerful enough to leave such a mark on the galaxy could have been caused by vast amounts of gas and dust falling into the black hole, or a huge, sudden burst of star formation nearby. An incident like this would have triggered an intense outburst of energy, whipping up galactic winds that violently drove gas and cosmic rays away from the galactic center. This would have stretched and amplified magnetic field lines in its wake, creating those bubbles and the non-thermal filaments. Furthermore, strong magnetic fields, which we now know are a confirmed feature of all the filaments, can trap cosmic rays. The great thing is, we can date them. The cosmic rays detected within the filaments by MeerKAT match the proposed timeframe of the Sagittarius A star outburst thought responsible for the radio bubbles. In other words, they are the same age. MeerKAT's position and capabilities, along with the same high-pass filtering used to resolve the filaments, not only revealed these bubbles in stunning detail, but also showed that almost all of the filaments are contained within them. With this hypothesis in mind, Yusef-Zadeh and the team described the formation of the non-thermal filaments as magnetized streamers in a cosmic ray-driven wind. It certainly paints a compelling picture for their possible origin, but it is not conclusive, as even the authors themselves acknowledge. Other theories are being developed. With a mystery this fascinating, other astronomers have been studying the filaments too. But this single MeerKAT image remains the one that has told us the most. But with so many unanswered questions, some going back 40 years, where does that leave us? Are non-thermal radio filaments just a galactic oddity? Not at all. They are a riddle wrapped in a mystery inside an enigma, and they could shed light on one of the biggest unanswered questions out there: how supermassive black holes regulate star formation within a galaxy. Scientists know that the active centers of galaxies must transfer energy and matter into interstellar space through a process called galactic feedback. If this didn't happen, star formation would run unchecked, using up a galaxy's gas and dust far faster than observations indicate. But how this feedback occurs is unknown. MeerKAT's detailed imagery of the non-thermal filaments and the radio bubbles provides compelling evidence that this outflow of energy could happen in discrete but extremely powerful outbursts. This is something that has been observed before. Fermi Bubbles, discovered by NASA's Fermi Gamma Ray Space Telescope in 2010, are even larger hourglass-shaped structures spanning a total of 50,000 light-years. These mind-bogglingly massive formations, often shown in magenta in images, are thought to be millions of years old. They were likely caused by a violent outburst from Sagittarius A star, which calculations suggest had the energy of 100,000 supernovae. This event was much more powerful and ancient than the one proposed to have created the filaments and radio bubbles. Together, they paint a picture of intermittent outbursts from deep within the heart of our galaxy. Both have the potential to regulate star formation, ensuring the Milky Way doesn't burn out too quickly. As scientists continue to unravel the mysteries of non-thermal filaments and tackle the big questions about how the universe works, the trail of discovery doesn't seem to be growing cold again anytime soon. Since that first full-array image, MeerKAT has found more of these mysterious strands in other galaxies, with very similar properties to the ones we see in the Milky Way. Their existence elsewhere suggests a common underlying mechanism and hints at their role in fundamental galactic processes. To conclusively piece together the whole picture will require another leap in imaging resolution. Hopefully, that is not too far off. MeerKAT, already honored by the Royal Astronomical Society for its spectacular radio astronomy observations, was built with longer-term goals in mind, specifically to be incorporated into the Square Kilometre Array. With a total collecting area of 1 square kilometer, it will be 50 times more sensitive than any other radio instrument in existence, and is expected to be fully constructed by 2028. Keeping an eye on developments in other parts of the electromagnetic spectrum will also be important. Yusef-Zadeh believes the next breakthrough will come from gamma-ray telescopes. Imaging at higher frequencies results in higher resolution imagery, which has the potential to show whether the filaments, the radio bubbles that contain them, and the vast Fermi bubbles are all connected. There is an elegance in order rising out of chaos. Observing non-thermal filaments streaming out through cosmic winds certainly fits that idea. So, keep watching this space. With images and phenomena this spectacular, it's certainly no hardship to do so. If you found this journey into the heart of our galaxy fascinating, make sure to show your support. Hit that like button, share this video with someone who loves cosmic mysteries, and subscribe to stay updated on all the incredible discoveries waiting just beyond our view. Through cosmic winds certainly fits that idea. So keep watching this space. With images and phenomena this spectacular, it's certainly no hardship to do so. If you found this journey into the heart of our galaxy fascinating, make sure to show your support. Hit that like button, share this video with someone who loves cosmic mysteries, and subscribe to stay updated on all the incredible discoveries waiting just beyond our view.